Hello. In this video, we are going to learn about improper integrals and how to integrate them properly. So there's a couple of different types of improper integrals. The first set of them deal with limits of infinity. So each one of these you can see has an infinity in the limits of integration. First one at the top going to positive infinity, and the second one to negative infinity, and then the third one has both limits of integration with an infinity in them. Now, the problem with this is that infinity is not a real number. I can't have infinity dollars, so I also can't have an integral that has an infinity in the limits of integration. Luckily, we have something that can help us get around that, and that is a limit. So with each one of these, whenever you see an infinity in an integral, you know you're dealing with an improper integral, and you know that you're going to have to use a limit in order to evaluate it. This is key. If I don't see a limit somewhere in your solution, then it's going to be a problem. If the infinity is in the upper limit, we will usually replace that infinity. Well, not usually, we will always replace that infinity with some dummy variable, just some made-up variable that's not being used in the problem. B is a common one that I use. And then I'm going to take the limit of this integral as that new variable approaches the infinity that I replaced it with. And so how I'm going to solve that then is to integrate the integral here, evaluate it at the limits of integration, and A is going to be an actual number, B will stay a B. And then once I've evaluated all that, then I will take the limit of that as B approaches infinity. So if you're feeling a little rusty on limits, it's a good idea to brush up a little bit for this section. If the limit is in the lower limit, I'm going to do the same thing. I'm going to replace that negative infinity with some variable, and then take the limit as that new variable approaches the negative infinity that I took out. If both limits have an infinity on them, that's when you get the most work involved. And I'm actually going to have to split this up into two separate integrals. And this C value, where you split it up, can be any number in between negative infinity and infinity. I usually use 0. It usually is just an easier one to evaluate limits for and integrals for. So that's usually where I split things up. So I would do an integral going from negative infinity to, say, 0, and then another integral from 0 to infinity, which means I'd go back to these top two and use those methods to evaluate the two separate integrals. Okay, and so once you evaluate that limit at the end of the problem, you're either going to get a limit that exists or a limit that does not exist. If the limit exists, so you get a real number like 5 or pi or square root of 2, then that means that the improper integral converges. And if you get something like does not exist or infinity, that means it diverges. So let's look at an example. So I've got this improper integral here. I picked the hardest one where I have an infinity in both spots, so we can run through that together. So I have the integral of x times sine of x squared dx. And so I'm going to split this up, just like I mentioned, at 0. So I'm going to do an integral from negative infinity to 0 plus the integral from 0 to infinity. I could have picked another value. I didn't have to pick 0, but it's just a convenient one. Okay, so now once I've got that split up, I can start replacing those infinities with a limit as some new variable approaches that infinity that I took out. And I'm going to evaluate each one of these separately. Now, looking at the integral, ignoring the limits and all that, the improper stuff that's going on there, I have x times the sine of x squared. That's going to require a u substitution to integrate. So I'm going to let u be the x squared that is inside of the sine function there, which means that du would be equal to 2x dx. And luckily, I have that x hanging out in front of the sine for each one of these. So I can divide the 2 over and take 1/2 du. I can add that in to replace the x dx. So after doing that u substitution, my two integrals look like this. So I still have my limit. I've got the 1/2, which I pulled out in front of the integral. You can pull it all the way out in front of the limit if you want. So I could do that for both of these and just have a 1/2 out in front of everything. Key is not to forget about that 1/2 later, because it might influence the value of the limit at the end. And then I have just sine of u du inside of each integral. Okay, so next step would be to actually integrate this. Okay, again, the limit part of this is going to be at the end of the problem after I've done all the integration and evaluated the limits of integration. Okay, so integral of sine is negative cosine, so I get a negative 1/2 cosine u for this one, and I'm going to evaluate it from 0 to a. Now, you might be a little bit rusty on evaluating definite integrals, so it's another thing you might want to brush up on for this section. And so I'm going to start by plugging in the upper limit and then subtract and then plug in the lower limit. So it's going to be negative 1/2 cosine of 0 minus negative 1/2 cosine of a. And then I'll do the same thing for the other one as well. Oh, wait, I forgot. Got to reverse my u substitution first. Oh, very common mistake that's easy to make. So I can't plug in u. These a's and b's and zeros. Those are all x values. So I have to reverse the u substitution, and then I can plug in my limits of integration. So I start with the top limit and then minus the second one. I have a double negative, so this turned positive. And same thing with the second integral. I've got a b and then a 0 for that one. Now, cosine of 0 is just 0, so those cosine of 0 terms just go away. They just zero out. And so really I'm just focusing on this cosine of a squared and cosine of b squared inside of my limits. So I can simplify it a little bit here, clean it up. And now is the time to actually evaluate the limit out front, since I did everything with the integral, and now I look at that limit. And here, I'm thinking about cosine. A is an increasingly large number, but if I think about the graph of any cosine function, it's just a wave that just goes up and down, and never approaches any particular value, which is pretty problematic for these. And I don't know, I had that extra step in there. That was unnecessary. But it turns out because neither cosine doesn't approach any particular value, so this limit does not exist. And so that means that this integral diverged. And that is my conclusion for this one. So I got a divergent a divergent improper integral here. Okay, so that's an improper integral that has an infinity on it. The other option is when I have an infinite discontinuity. These are a lot harder to catch. You really got to be paying attention to either what the graph looks like on the interval or just really looking at that function and the values inside the interval. And I've got a graph here on the right of what this can look like, where I have some kind of vertical asymptote that's going off to infinity or negative infinity at here. This specifically is at an endpoint, but we will also look at if it's in the middle of the interval. So this one has an infinite discontinuity at the upper endpoint here at b. And how I deal with that is I do a limit again, only this time I'm going to do a one-sided limit. And this usually doesn't end up mattering too much, but it is a technicality that should be accounted for in your problem. We're taking a limit from inside the interval, so that means I'm coming at it from the left side. So that's why I have this b minus here. This is a left-handed limit. And I've replaced the point, the x value that is discontinuous, with some new made-up variable that's not being used in the problem. And I take the limit as that variable approaches b from the left. So that's if it's on the right side of your interval. And again, just like before, if the limit that I get from evaluating this exists, then it converges. Otherwise, it diverges. Here's an example where the discontinuity is on the left side, so the lower endpoint. And so same idea, I take the value where the discontinuity is and I replace it. And with this one, from inside the interval, I'm coming at that value from the right. So this is a right-handed limit. So I put that little plus there to indicate that. Worst case scenario, most work, is when it's somewhere in the middle. These are also the hardest to spot because you don't actually see the value where the discontinuity is. It's just somewhere in between A and B where you have a discontinuity. And so for this one, it's much like when you do an integral from negative infinity to infinity. I have to do each piece separately. So I have to do an integral for the left side of this. And so that would be a left-sided limit coming at it at C from the left. And then I'd have to do one for the right side. So a right-handed limit coming at C from the right. So it's like a combination of those first two examples with infinite discontinuities. Okay, so let's do an example of this one before we leave for the day. So we want to evaluate this improper integral. And again, there's nothing there jumping out at me telling me that this is improper because I don't see an infinity or anything like that here. I'm not looking at the graph. So I really just have to pay attention to these and think about what unit I'm in is also a good indication. So I have this x minus 1 in a third root in the denominator. And my interval starts at 1. So if I were to plug in 1 here, I'd get 0 in the denominator. That's going to result in a discontinuity, and that's what makes this an improper integral. Again, it's really subtle, easy to miss, but that is why this is improper. And so that means when I go to solve this, I'm going to have to replace the 1 with some new variable and then take the limit as I approach from the right, as I approach 1 from the right. Okay, so we notice, okay, I have a discontinuity at x equals 1, which is in the interval. If it was out of the interval, no problem, but it's in the interval that we're looking at. So I now have the limit as a approaches 1 from the right, and then the integral goes from a to 2. Again, this limit is necessary to solving this problem. It needs to show up in your solution. Okay, so now I can focus, now that I have that limit added in there, I can focus on how I would actually evaluate the integral. And again, it's going to require u substitution. So I'm going to let u equal the x minus 1 that's inside that 1/3 root. And that means that the derivative would be just of x minus 1 would be 1. So du equals dx. Doing that substitution, okay, I've got my limit still hanging out front. And I rewrote this using a negative exponent. Just easier for me to do the power rule that way. So u to the negative 1/3 is what I'm integrating. So I add 1 to the exponent, which is going to give me a 2/3, and then divide by that new exponent. So divided by 2/3 or times 3/2. And then I don't want to forget about those limits of integration. So just like before, I plug in the 2. Or actually, I almost did it again. Reverse your u substitution. Okay, so plug in that x minus 1 again. And now I can plug in the 2 and the a. So I end up with all this here, 3/2 times 2 minus 1, which is just 1 to the 2/3, and then minus 3/2 times a minus 1 to the 2/3. So I can simplify that first one. I get just 1 to the 2/3, which is just 1 times 3/2. So that becomes 3/2. And now I can finally evaluate the limit as a approaches 1 from the right. Now, the nice thing is here, I can just plug in the 1 as long as it's not going to create a discontinuity, which because my exponent is now positive, I have no issue. So you can just plug in 1 for a and simplify. So 1 minus 1 would end up giving me a 0. For this whole second term, just zeroes out, and I end up with just the limit of 3/2. So I get 3/2 for the limit. I got a real number, so I know that this converges. And there it is. I got my answer. Okay, so we saw an infinite discontinuity and an infinite limit example. Here's one more for you to try on your own.